let's talk about invariant distributions for a little bit more. Now we've managed to compute one, so we have a little bit more of an idea of how it works. And I want to give you a bit of an interpretation. This is kind of my take, but I think it works pretty well. Is that a good way of thinking about things is that the invariant distribution represents how much the Markov chain wants. Obviously, it doesn't have a will, but in some sense, the emphasis that every state will have. So a state with a high value is a state that it wants to visit a lot, so it will visit it a lot, and a state with a low value will be visited less often. Let's go back to our example, actually. So we had this, and the values that we had, hold on, the values that we had were, put those in green, 3/8 for A, 1/4 for B, 1/4 for C, and 1/8 for D. So in particular, you see that the value for A is triple the value for D. That's because it's pretty hard to get to D, right? The only way that you're going to actually get to D is by getting to A first, and then you have your third chance. Obviously, pretty low. Meanwhile, it's pretty easy to get to A because you could start from anywhere else and you'd get a decent probability of getting there. And again, B and C have the same value because the chain will want to go to one or to the other at exactly as much given the whole symmetry thing. So that's really what this whole wanting thing means. Let's go back to our slide. So you can use it to sanity check your results. Actually, I'm going to use this. Go back to the example again. Sanity check. Okay, we make mistakes all the time. Everyone makes mistakes in math. So sanity check is often a good thing to do whenever you compute something. Here, I found a much larger value for A than D. That makes sense. I want to talk about one mistake that people do quite often. I've seen it happen quite a bit, is once you end up with this, some people on accident, and anyone might do it on accident or by accident, kind of will invert things and will end up with saying that like value of pi A will be a third of the value of pi D instead. So kind of mixing things up because A needs to be an eighth, so there's an inversion here from the eighth, which is the total sum of these. So be careful. And remember, if I have 3A here, it means that A value of pi A is triple value of pi D, not the opposite. So again, sanity check. A is more easy to visit, so it should have the bigger value. Good. Very good. So we have this. Quite happy with that. And we have quite a few more things to say about invariant distributions. Let's talk about infinite state spaces. We won't be playing with these too much in this chapter because, mostly because it's a bit harder. But I think there are a few questions in the exercise list which have some. So what happens if your state space is infinite? Well, in principle, the same things happen. So you have the same sets of equations because you can still multiply infinite matrices in that sense. It's a bit harder to interpret, but it does happen. Now, of course, we are getting infinitely many equations because there's as many equations as rows of a matrix. And also, since each equation is a column, the equation itself might be infinite. So yeah, possibly a bit hard. And because of the infinity, sometimes there won't be solutions to your system. Oops. Big oops. So somehow, even though we know 1 is an eigenvalue because it's an eigenvalue on the right, we might not be able to find an eigenvector on the left. That's a bit awkward. That happens because of infinity. Sometimes there's just no invariant distribution. But that's okay. We just need to live with it and do what we can. Kind of related to infinite state spaces, let's talk a little bit about transient states. So you'll remember, why is this related to infinite state space? Because if you're irreducible and in a finite state space, then no one is transient. Everyone's going to be positive recurrent. So if we want to have a meaningful Markov chain with properly transient things, you're going to need an infinite state space for it to be irreducible and yet transient. And we've talked about the random walk. So here's a useful proposition. If I take my Markov chain, I take any transient state, then we're going to show that the probability of being equal to I, so pi n I, will tend to 0 as n tends to infinity. So the probability of getting there tends to 0, so less and less likely to be there in some sense. And as a consequence, any invariant distribution will give you a value of 0 for that state. And as a further consequence, there's no stationary distribution. Okay, this is pretty strong. Before we prove it, a few comments. Pi I equals 0. I just told you that pi I represents how much the Markov chain wants to be at state I. And of course, if state I is transient, it means we might leave and never come back. So it doesn't really want to come back at all. It doesn't want to be at I. Hence, there's 0 here. If it does come, it will only come a few times and never again. And furthermore, there's no stationary distribution. So that means in particular, if you remember, like we talked about the random walk in chapter 3, and we said that in the case where it's not fully symmetric, so you're more likely to go up or down, then it's transient. This means that in those cases, it has no stationary distribution. More on that in a second. For now, let's prove this, because this is a useful thing to have. All right, let's go. And before proving it, this is a proper proposition. We'll write it down. Proposition 19. Wow, it gave me a straight line even though it's diagonal. Great. So let I be any transient state. In fact, transient state. Then probability that xn equals I tends to 0 as n tends to infinity. Remember, this arrow means it's a limit, basically. Consequence. As a consequence, for any invariant distribution, pi vector, we have pi I equals 0. And the further consequence, which is not in the lecture notes, let me quickly check again on the slide. That's okay. I'm realizing there's a tiny mistake here. Okay, there's a mistake. This slide is bad. The slide will be fixed when you see it. But right now, this version of the slide is bad. So there's no stationary distribution for an irreducible and transient Markov chain. The word irreducible is missing on that slide. I knew something was wrong. So furthermore, if we are irreducible and transient, there is no invariant distribution. Distribution. Okay, technically there's 3 things, so we'll prove all of them. Let's go. And you know what? Sure, let's give these little letters A, B, C. Let's go ahead and go. Proof. A is the main one. B and C are just consequences. So I is a transient state. Let's take it again. let I be a transient state. So what I know about transient states is that I'm going to visit them a finite number of times. Eventually we'll reach the last time and then never come back. So for this reason, we're gonna let capital T, it's gonna be a random variable, be the time of the last visit. Let's put final instead of last to make it quite clear. Final visit to I. I'm going to call it Ti, like in the lecture notes. Here it doesn't quite matter. So T is a finite random variable. I'll write it. Is a finite random variable. Okay, so what did we want to do? Reminder, we wanted to show that the probability that xn equals I tends to 0 as n to infinity. And notice a simple thing. Notice that probability that xn equals I is smaller than probability that Ti is larger than or equal to n. Why is that? Why is that? So if xn is equal to I, it means I'm visiting my state I at time n. So the last visit might be n, or it might be later. But it's certainly not going to be earlier, because we're there right now. So that's it. Last visit has to be n or further. Now, why is this great? So we said that Ti is a finite random variable. If you think about what this means, now the probability of being larger than n should get smaller and smaller as n gets bigger and bigger, because we're removing more and more possibilities. And it is a fact that this probability that Ti tends to n, this tends to 0 as n tends to infinity, because Ti is finite. And that's just a fact of finite random variables. If you want, you can write this as this is equal to the sum for k going from n to infinity of probability that Ti equals k. And this is the remainder of a convergent series, and you know that the remainder of a convergent series, that tends to 0. So that's one way of seeing why. But that's just a fact in general for any finite random variable. Okay, so if I'm a probability, this thing, and I'm smaller than something which tends to 0, then basically by the sandwich theorem, I can put like 0 here. And the sandwich theorem, which will tell us that the middle has the same limit as the two sides because they already have the same limit. So let's do it this way. By the sandwich theorem, very useful tool. That's an A. Probability that xn equals I tends to 0 as n tends to infinity. Okay, good. So we have the A part, which, as I said, is really the main part of the thing. Now, let's do the B part. The B part was that any invariant distribution gives a 0 value to I. Now, let pi, underlined, be an invariant distribution. Now, we're not even saying that pi exists. In the C case, we will see that there is no pi. But if we have one, what happens? That's an R. Sorry. There you go. So we're going to run the chain starting from pi. So run the chain starting from pi. So this means we take pi 0 equals pi. Then we know by invariance, by stationarity, since we are in equilibrium, I will say, in equilibrium, we have that the probability of being at I at time n is equal to pi I for all n. This is what equilibrium is. This depends on n. Actually, it doesn't. It's always equal to my pi I. And that's, it's not a capital letter. Let me make it small. Like this. And now we can just use part A. It's refusing to let me erase. There you go. Let's use part A, and we can take the limit. Okay, we know that this converges to 0. By part A. So taking the limit, we get indeed that 0 equals pi I. And we're done. Nice. Nice indeed. So now you know an invariant distribution gives a 0 value to any transient state. Finally, part C, where if we're irreducible and transient, what happens? So in the lecture notes, it's not part of the proposition, but it's just afterwards. So just see, it's just after the proof, so it really is an extension. Then we would need, an invariant distribution pi as we've shown. It would require to have 0 values everywhere. Pi I equals 0 for all I. But it still needs to be a distribution. It still needs to add up to 1. So, and sum for I and S of pi I equals 1. That's impossible. So there is no invariant distribution. And you know what? That's okay. That is absolutely okay. So one last thing for this bit of video, one final slide, which might surprise you. So, oh, there you go. There's the consequence. Okay, so yeah, strike this from the proposition, really, is probably the way to do. I will tweak the slides so that they're fine later on. Sorry about this. Actually, the result of this theorem is still true if we are null recurrent instead of transient. So it's a bit harder to prove. And that's why I'm not going to do it here. It will more or less come out as a consequence of other things that we'll be doing later. So another reason not to prove it here. The main reason we did prove the transient case is that it's going to be useful for the next theorem, which you will see in a bit.